Hello everyone, welcome to CSEN 503, Introduction to Communication Networks. This is Dr. Amr El-Mugi. In the last lecture, we finished our discussion of the transport layer. We discussed TCP and UDP. Our discussion focused on TCP and the services within. We discussed port numbers, we discussed reliable delivery, we discussed flow control and congestion control. And this actually ends our discussion of the transport layer. Today we are going to go one layer below in the protocol stack and we will start the discussion of the network layer. We studied application layer, we studied the transport layer, and today we are going to start the discussion of the network layer. And I would say the network layer is actually very interesting in computer networks because it's where all the magic actually happens, where we will learn how the packet actually makes its way from source to destination. We know that the protocol stack has 5 layers. We have studied application and transport. We are now in network. There's also data link and physical. And we know that the nodes that implement the full protocol stack are actually the end nodes that, as we see here. The routers on the middle implement only the bottom 3 layers of the protocol stack, namely physical, data link, and network layers. So once a device generates a packet, it's generated at the application layer, goes to the transport layer, which adds the transport layer header, TCP header, for example, then to the network layer, which adds the network layer header, which we will see shortly, and then to the data link and then physical. It gets sent. The routers will do routing based on the network layer header, the IP addresses basically, which will determine how the routers will forward the packet. And then the packet may go over several routers from source to destination, as we see here. And in every router, the network layer is going to determine how the packet will be forwarded until it reaches the destination. The destination, because it will be an end device, will have the full protocol stack. And so the packet eventually will reach the application layer at the destination. Okay. How do the routers actually do forwarding? The routers have no concept of a connection, meaning that if you have a virtual connection between the transport layer in A and the transport layer in B, the routers are completely oblivious of that. The routers do not know anything about a connection at the upper layers. To the routers, every packet is independent. They treat every packet independently. So when a router receives a packet, it looks at the IP addresses, the source and destination IP address in the packet, and uses this information along with its forwarding table to determine how a packet will be forwarded. So every router will have a forwarding table that contains basically a list of destinations and a corresponding physical port. The table basically said if the destination is X, put the packet on port 1. If the destination is Y, put the packet on port 2, and so on. Okay, so the router will use this table to figure out how to forward the packet, and the process is done independently for each packet. As we see in the bottom figure here, this means that each packet from the same source to the same destination can end up actually following different paths. So the first packet may follow this path, the second packet may follow this path, the third packet may follow this path, and so on. What would actually make a router to change its decisions about how to forward the packet? This is based on the router's continuous operation of what is called the routing protocol. The job of the routing protocol is to figure out what is the best path from any device to any other device. In reality, its job is to actually figure out the best path to any destination. And so when it receives a packet, the routing protocol will tell the router what is actually the best path to this particular destination. Okay? And we know that networks are dynamic. At one point in time, this router here may be congested. And so it will then impose a large delay over the path of the packets which flow through it. At another time, this router may not be congested at all, and so the delay will be low. The routing protocol continuously operates to figure this out. Figures out that at this time, the bottom path is actually the best one. While later, because delay happens at another router, the best path could be a different one. And for this reason, because networks are dynamic and because queuing delay is dynamic and because routers cannot estimate when anyone will actually send a packet, the routing protocol will continuously update the routing tables to reflect what is the best path from any device to any other device. And so, for example, if this router starts to lose packets, this router here will figure out that there is a high delay over this path, and so it will start to forward packets over a different path. Okay. To understand how routers work, we have to understand a difference between two key functions in the network layer. These are routing and forwarding. And to understand them, I will give you actually an analogy, which is Google Maps. If you have used Google Maps before, you will know that in order for you to find a path to any destination, first thing you will do is actually enter the destination address here. Google Maps probably detects your current location on your own. You can set a starting location and you enter your destination, and then Google Maps will figure out a path for you, as you see here in the left figure. Google Maps may actually figure out more than one path. Could tell you that this is one route, there is another route that has maybe a shorter distance but longer delay, and you have to choose one. Once you choose one and you click start, you go to the view on the right figure. The view on the right figure is no longer the map. The view is actually just to the next transition. So here it tells you that in 110 meters, you are going to turn left on something called Zachary Lane. Okay. Once you make this left turn, Google Maps is going to update and it's going to tell you what is the path to the next intersection or the next transition. This is actually the difference between routing and forwarding. Routing is what you do on the left. You figure out the entire path. So the routing protocol figures the entire path, the full list of routers from source to destination that will actually achieve the optimum routing metric, for example, delay. You may have more than one path from source to destination, but at the end you choose one. Once you choose one, you go to forwarding. This is what every router does. So forwarding basically tells you what is actually the next hop. So in a router, if it has several ports, the forwarding table will just tell you which port you should put the packet on. Obviously, the forwarding table is populated using the routing protocol. So the routing protocol first runs, figures out the best path to the destination, and then fills the forwarding table. And then the forwarding table is the one that is going to be used to do forwarding. Just as we see in this figure, the routing protocol figures out the entire path. The forwarding table on the right just tells you the next intersection. So how does routing actually work? We'll see it in details later, but just for now, the entire map or the entire network topology is drawn or is seen as a graph where the routers are the vertices on the graph and the edges connect the vertices that can actually talk to each other directly, and the routing protocol will figure out the set of links that have the minimum total cost. Okay, so what does the forwarding table look like? If you have the network that you see in this figure, we see here the routing algorithm figures out what is the best path and fills in the forwarding table, which we see here. What is actually saved in the forwarding table? The forwarding table is not actually indexed by specific IP addresses, but rather they're indexed by a range of IP addresses. So one entry in the forwarding table will say, if the destination IP address is from this value to this value, meaning that the destination IP address in the packet is anything between these two values, put the packet on link interface 0. If the destination IP address that you receive in the packet is anywhere between this value and that value, put the packet on link interface 1. If the destination IP address in the received packet is anything between this value and that value, put the packet on link interface 2. And this is what this router is actually going to do. It's going to receive a packet, it's going to look at the destination IP address, and will figure out which range this destination IP address flow of is in. Every router will also have an entry that is called the default route. It's basically an otherwise entry, meaning that if the destination IP address in the packet is nowhere within the ranges that are saved in the forwarding table already, there is a default route. There is a default interface. Basically, this router then will give the packet to another router that has more information about how to forward. We had discussed this previously in one of our earlier lectures, We said that the example of the mailman, for example, if you're sending a letter from Cairo to someone in Australia, the mailman that receives your letter in Cairo doesn't have to know where is the exact address in Australia. The mailman only needs to know that it is not within my immediate service area. So the mailman will have a default route, will have a pile, for example. Any letter that is going outside my service area, I will put actually this letter on this route. Routers will do the same. If they receive a packet and they have no idea where the destination IP address is, they will use the otherwise entry, which is called the default route. Okay. Now, I want you to take a look at these two top and bottom parts of the range. So this one starts with 11001000, and you see here this value here, okay, is the same as this value here. This value here is the same as this value here up to this part. Okay, so from this part until actually the beginning, the top and bottom ranges are exactly the same. So if they are exactly the same, this is actually the only part that you need to save. And so the forwarding table actually becomes that. So this entry here, if we count the number of bits, they are 1, 2, 3, 4, 5, 6, 7, 8. And then another 8 is 16, 17, 18, 19, 20, 21. This entry here contains 21 bits, while the IP address is actually 32 bits. So what happens to the remaining 11 bits? That doesn't mean that the packet has only 21 bits. It means that I only care about the first 21 bits of the packet, the ones that are in the most significant positions from the left. The second entry in the routing, in the forwarding table, has 24 bits. And the third entry also has 21 bits. So the entries in the forwarding table are never actually, or are very rarely 32 bits. They are a number of bits that reflect a range. What does it mean to have an entry in the forwarding table that is only 21 bits? It means that this entry is valid, or I can use this entry as long as the first 21 bits of the packet are the same as the ones in this entry right here. When do I use the second entry? When the first 24 bits of the IP or of the destination IP address in the received packet are the same as this entry. When do I use the third entry? Meaning when do I put the packet on link interface 2? If the first 21 bits in the third entry are the same as the destination IP, are the same as the first 21 bits in the destination IP address. This is not actually the end of the story. If you look at these three entries, you will notice that up till here, all the first 20 bits are actually the same. Okay, starting the 21st bits, the IP addresses or the entries in the forwarding table may become different. Okay, that means that what happens if you receive a packet with the first 20 bits the same? Okay, which entry you would use? As a default rule, routing tables use the longest prefix match. Longest prefix match. Meaning that when a router receives a packet, it will use the entry in the forwarding table that best matches the destination IP address. And the one that best matches the destination IP address is the one that matches with the largest number of bits in the entry, in the forwarding table. So let's say you receive a packet that contains a destination IP address with the first 24 bits the same as these 24 bits. This will mean that the 24 bits are exactly the same as this entry, but it will also mean that the first 20 bits are the same as the first, second, and third entries. Why did we use the second entry? Because it's the longest prefix match. It matches with the largest number of bits. Okay, so if you receive a packet and the destination IP address has the first 20 bits, the same as any of the three entries, while the 21st bit is 0, you will directly use the first entry in the forwarding table, putting the packet on link interface 0. If you receive a packet with the first 20 bits, the same as the three entries, but the 21st bit is 1, you can use the second or the third entry, but you will look at the 22nd entry. If the 22nd entry is 0, you will look at the 23rd entry. If the 23rd entry is 0, you will look at the 24th entry. If it is also 0, you will use link interface 1. However, if the 22nd, 23rd, or 24th entries were not all zeros, you will then go and use the third entry in the forwarding table, putting the packet on link interface 2. So the only way to use the second entry in the forwarding table if the entire 24 bits of the destination IP address would match. What is the intuition behind that? What is the intuition behind the longest prefix match? Imagine you have a network. Let's say you are sending a packet to someone at the Faculty of Computer Science within the network of GIUAS. If you know only the address of GIUAS, okay, that means you know only a good path to the network of GIUAS. If you know a good path to the Faculty of CS in GIUAS, that means you know a better overall path. So the more information about the destination, the longer the prefix match will be, and so the better information you will have about the routing path. And this means that if you use the longest prefix match, you are actually using a better path to the destination in this case. Okay. Now we can actually take a look at what this network layer includes. How does the network layer actually achieve its functionalities? In every layer that we have discussed, we discussed the main protocols that we find. So in the transport layer, we discussed TCP and UDP. These are the main two protocols that we find in the transport layer in the internet. In the network layer, the protocols actually fall into categories. You have something called the ICMP protocol, the Internet Control Message Protocol. It is mainly used for signaling and error reporting. Signaling means if the routers wish to communicate with each other. If you have ever tried something called ping, ping is actually a test packet. When you send the ping packet, the destination returns the ping to you, and you can measure the difference in time to calculate the delay between you and any other device. Okay. The ping packet is actually part of the ICMP protocol, and there is a large number of other types of packets that are also part of the ICMP protocol, all used for error reporting and signaling. Okay. You also have at the heart of the network layer routing protocols that are always running. They determine the best path from source to destination, and we will discuss their categories later. Today, we will start the discussion with the most important protocol that we have in the internet, which is the IP protocol. And it is very important because it defines the structure of the IP header, and defines the structure of the IP address. How does the internet work? How do routers are actually able, or how are routers able to forward the packet from any device to any other device? Because all the devices on the internet are following the same addressing convention. All the devices are using the same structure of IP addresses. Okay, if everyone follows the same addressing convention, then all the routers will be able to understand what an IP address is and what it looks like. Okay, when you send a packet, when you send a letter using the regular mail system, you write the address in a specific format. It's street number, city, country, and then you have the postal code, for example. This is the addressing format. The IP protocol also defines an addressing format for the source and destination IP addresses. And if everyone follows it, then the routers will be able to figure out how to forward a packet. And this is basically what the IP header looks like. So far, we have discussed what the application layer data looks like, for example, an HTTP request or response. And then we saw what the transport layer header looks like, all the fields within, the acknowledgement number, sequence number, the flags, the urgent pointer, and all of that. And this is then what the IP header looks like. These are all the fields in the IP header that are added to the packet at the network layer. Starts with the version field. In IP, there is either IP version 4 or IP version 6. This header that you see in this figure is IP version 4. We will actually discuss IP version 6 later. It is still actually the most commonly used version of the IP protocol. And if you're using IP version 4, the version field will say that this is version 4. Okay. The next field is called header length. It specifies the length of the header. Why do you need to specify the length of the header? Because there is a field that is called the options field. The options field actually may have variable length. You can enter different types of information. For example, the timestamp. You can enter a list of IP addresses of all the routers over which this packet has traveled. There are many things that you can do. By default, it's empty. And if it's empty, then the size of the IP header will be only 20 bytes. Okay. So if you have an options field, then depending on how long the options field is, you may have a longer IP header. In any case, the header length specifies everything in the IP header, including the options field. Then you have the type of service. This is basically mainly used for quality of service. If you have, for example, a packet that is real time and you want the routers to prioritize it, you can enter a specific code here. Then you have the length field. The length field is actually the length of the entire packet, including the network layer header, the transport layer header, and the application layer data as well. This is what is specified by the length field. Now you will see here that the length field is actually 16 bits, meaning that the maximum length of the packet is 2 power 16, which is equal to 65,536. This is bytes. So the maximum size of a packet that can be sent over the network is actually 2 power 16 minus 1, so it's 65,535 bytes. Okay, this is the maximum size of a packet that can be sent over a network. Okay, the following three fields, they are the 16-bit identifier, you have a set of flags, and you have the fragment offset. Those three things are used for something called fragmentation, which I will discuss in a little bit. Then you have something called the time to live field. The time to live field is basically a counter. Whenever a packet receives, whenever a router or a device receives a packet, it will decrement the time to live field and send the packet to the next path, to the next hop. This, or the intention, the reason behind that is that you don't want a packet to keep looping around the internet forever. If you don't have a time to live field, then there is nothing that would prevent that. If every router would decrement the packet, then even if you have loops in your network, eventually it's going to reach a device where the time to live field is 1, then it's going to be decremented to 0, and then the router will have to throw this packet away. Okay. The next field is called upper layer. This one actually determines what is the next layer that I will give the packet to at the destination. So at the destination, we know that we have the physical layer, then you have the data link layer, and then you have the network layer, then you have the transport layer, okay, and then you have the application layer. So when the packet finally reaches the destination and it makes its way up physical data link and then it reaches the network layer has to figure out which transport layer protocol I'm going to give the packet to, either TCP or UDP, for example. And so if the transport layer header is TCP, then the upper layer field is going to include a code that says TCP. If it is UDP, it is going to include a code that says that the upper layer is UDP. Then you have a field that is checksum. It is used to check for errors. It's just a method to check for errors. The routers don't actually react to errors. They don't retransmit. There is no retransmission mechanism. The header checksum is sort of like the parity bit that we discussed in the technical foundations course. And then you have a 32-bit source IP address, and then the 32-bit destination IP address. Okay. Okay. Last thing that we will discuss in this lecture is something called fragmentation. So whenever the application layer composes data and gives it to the transport layer and creates a segment, the network layer has to figure out what would be the size of the packet that is sent over the next link. At the transport layer, we said that there is something called the maximum segment size. This is the maximum amount of data that the transport layer is allowed to put in a single packet. The network layer also will observe another parameter that is called the maximum transmission unit. This is defined by the network that is being used. For example, if you are sending data over an Ethernet network, okay, then the maximum size of a packet is actually 1500 bytes. Okay? If you are sending it over a different type of network, there may be a different maximum size for the data. And so What would happen in this scenario? Let's say you have a router. The router receives a packet that has a size 2400. Okay, so it's 2400 bytes, including 20 byte header. And the MTU, the maximum transmission unit size over the link at the link over which the packet is received, is 4000, as we see here. Okay. However, the router needs to output the packet on a link that has MTU 1000. So the router receives the packet over a link that has MTU 4000 and wishes to output the packet on a link that has MTU only 1000. So what would it do in this case? It cannot actually send the packet right away because the maximum transmission unit size of the outgoing link is smaller than the size of the packet. So if the router receives the packet that is 2400, it wants to send it over a link that has MTU 1000, it has to fragment the packet. It has to basically split the original packet into smaller fragments and send each fragment as an independent packet to be routed by the router. Okay. Now, if the original packet is to be fragmented, somewhere in the network, they're going to have to be reassembled. This somewhere is actually the very final destination. The final destination, the very final, not the final router even, the very final device is going to receive all these fragments and it is going to reassemble them. What happens is, let's say this is the final destination of the packet. Once it receives the first fragment, it will start a timer, and the timer is typically between 60 seconds and 120 seconds. If it receives all the fragments of the packet, then it's going to reassemble these fragments and give the packet to the transport layer. If even one fragment is lost, then the end device is going to throw all the remaining fragments away and leave it up to the transport layer to recover from this error. So in any case, somewhere over the network, let's say this router will divide the original packet, sorry, it's actually this router, will divide the original packet into 3 smaller fragments, okay? And all these fragments are going to be sent over the network as independent packets, and the final device is going to reassemble them if it receives all the packets. Because every fragment is transmitted independently, maybe one fragment will be lost, maybe the 3 fragments are going to be delivered, but they're going to be delivered out of order. Maybe the 3 fragments are going to be delivered one after the other. There is no way of telling because they are treated as independent packets from this point on until the destination. Anything can actually happen to them. And so the network layer needs a mechanism to achieve that. So how would the destination device, first of all, know that it has received fragments belonging to the same original packet? That's question number 1. Question number 2 is, how would the destination device reassemble the packets? How would it know that this is actually fragment 1, this is fragment 2, this is fragment 3? As we said, the fragments can actually arrive at the destination out of order. So the destination device needs to be able to reorder them. All this information is actually in the network layer header. There is, as we said, a 16-bit identifier. This acts as a sequence number for the packets. So whenever you send a new network layer packet, it is going to have a new 16-bit identifier. Obviously, they have a finite number, and so they will recycle. Okay. Once you fragment a packet into smaller fragments, all the other fragments are going to have the same identification number. So here we see the original identifier was 428. You see the 3 fragments that are generated. All of them are carrying identifier 428. So if the receiver receives these 3 fragments, it will know that they are fragments because all of them are carrying the same identifier. If it were a new packet, it will carry a new identifier. It will be, for example, numbered 429. So the receiver would know that this is a different packet. Okay. How would it then reorder them? Through something in the header that is the fragment offset in addition to the flags. Basically, whenever you receive a packet, whenever you generate a packet, by default, the fragment offset is set to 0, meaning that this packet is not fragmented. Once you generate a fragment, first of all, the fragment offset will start to change. The fragment offset is now as we will explain in a little bit, determines the order of the packets. And there is also a flag that says more fragments, or the MF flag. If the packet is fragmented, the MF flag will be set to 1. Okay. Only in the last fragment, the MF flag will be set to 0, indicating that this is actually the last fragment. So if the MF flag is set to 1, it means that there are more fragments to come. So if you receive a fragment that is set to 1 with the MF flag set to 1 and fragment offset is set to 0, it means this is the first fragment, because this will be the only fragment where the MF flag is set to 1 and fragment offset is set to 0. If you look at the original packet, both MF flag and fragment offset are set to 0. Only the first fragment will have MF flag set to 1 and fragment offset set to 0. If you receive a fragment with MF flag set to 0 and fragment offset to a certain value, you know that this is the very last fragment. So now you can figure out the first fragment and the last fragment, and everything else will be in between. Now the only thing that remains is to identify what is the fragment offset in each fragment. Okay. I think we will not have time to finish this in this lecture, and so I will stop here and we will go over this example again in the next lecture. Stay safe and we'll talk to you next time.